And this is my draft book. However, I will do it slowly. As we teach you, I also will improve the book. Okay, let's look at what there is two annexes that we use in the aircraft industry. We use Annex 8 of International Civil Aviation Organization and Annex 6. Annex is standard and recommended practices for all the member states. All the states that become a country, become the member of ICO, International Civil Aviation Organization, they have to follow the standard policy and recommended practices. Those are in the annexes. There are 19 annexes, and that what related to us here is two annexes, which is Annex 6, Aircraft Operation, and Annex 8. Annex 8 has been translated into Malaysia regulation into CAM, Civil Aviation Authority of Malaysia, CAD number 8 and CAD number 6. So those document has been translated into Malaysian regulation. Okay, what interests us is the definition of repair. Repair is restoration. You can see both having the same meaning, restoration. We restore. We restore the strength, we restore the look, we restore the shape. Whatever we can restore, we restore to the original as much as we can. So those are repair. So that's how we define the repair. Okay, next is about introduction. So what you need to do, you need to brush up your mechanics of material, which we have learned, I think, a few semesters ago or last semester, because this subject is the application of the mechanics of material. So whatever you learn in the mechanics of material is applied in this aircraft structure repair. So that is how important is the knowledge on the previous mechanics of material, as well as I think you make mechanics of solid, which is some university call it static and dynamic. So those are the basis. You need to be conversant, you need to be competent for you to understand the subject better. So let's look at the material. We review the material having strength, and each material will have this curve, stress and strain curve. Why we have this curve? Because we tested the material by applying forces. For the tensile, we pull it until the material breaks. So as we pull, apply the load, you got the stresses. So the stresses also will be that has a direct effect by strain. Okay. Stress and strain. Strain is the elongation or deformation divided by original length. So how much deformed? So it is deformed in 1 mm. Divide the length. If the length of material is the part is 100 cm, you divide 1 divided by 100. The value that you get, that is a strain. So this is strain versus stress. Stress is force over area. As you apply the load, the structure deform. So it deform, continuously deform. Then until a time where it's no longer deform linearly, this is linear, then it start to yield. Yield means you don't apply the stress, however, the structure is continue to elongate, or you can say also creep. Then we apply very small load, and we get small stresses, however, the elongation is more easy to pull those material apart. So those are the strains. So until it break a point where we call ultimate stress. So here is a point where the stress is highest and where it breaks. So that is the maximum stress or fracture point where the material will be breaking, will break off. So we have learned this in your mechanics material. Any question on this? Okay, now we go to 1.1, 1.2, loads. Load is very important in because what we do in the aircraft structure repair, we have to determine the load on the structure. Divide by the area, you got the stress. So the stress that you have, compare back to the material stress. So the material here will have many of these. Each material will have the same figure. I mean, not the same. We'll have this kind of data, and then we able to determine the ultimate tensile strength of each for each material. So here this curve here is available for any material, including biomaterial, like you will talk about bone, talking about tissue. They also have value for this because they has been tested for this. Okay, loads. Load is something that important. Without load, you don't get the stress free. But however, in life, anything that you do, there's a load. So there are compression, there's axial load, which is tension and compression, because the load acting parallel to the part, we call it axial. So axial forces, which is tension and compression. And also we have bending. And then we have shear, torsion, and combined loading, which is axial and torsion. So aircraft also will have the experience loading. They also have tension, the compression, bending, shear, torsion, and combined loading. We do see that on the aircraft. So that's why we have to care about this load. We have to determine which part of the structure having the load, so we are able to do the stresses easily. Okay, questions? You have learned this before. Then stress. We got load, we got stress. Because it's very simple. Force over area is a stress. So we have tension stress, compression stress. For the axial load, we have torsion when you twist the thing, and you have shear if you're trying to cut the material into two, we're shearing off, and also bending. So this is basic stresses. Anything that you do, anything that you analyze, this is the stresses that we need to look for, and these stresses also are correspondent to the material. Each material will have the strength for each of these stresses. How they get it? Through the test. So what we do, we try to work out the stresses for each part and component and determine whether they are safe or not. We call it, we should have like 50% over the limit load. The load that you apply in service is limit load. Or as the structure will not be certified. So let's look at the tension and compression. It's axial load. We do have the formula force over area. The area will be area perpendicular. Area perpendicular means this is the force here 100, perpendicular is 90 degrees to the force. So the A here is the area 90 degrees to the force that you apply. By doing that, you have axial stress. So in this case, the load is compressed, and we have the compressive stress, compression stress on the part. And the unit will be in the Newton meter square, which is Pascal. So you can see PA after the number, that is Pascal, that is pressure. Okay, and the load, there's another failure. Load failure, if you compress, if you pull, if you compress, is squash, and you can cut the material into two. And also you can pull, cut also into two. And also there's another stress which is not really, it's not related, but always been used, is buckling and wrinkling. Or crippling, sorry. Buckling and crippling. Buckling is you apply load on the structure start to bow or deform sideways. So those are buckling. But if you see the structure deform, localized, wrinkle, those we call it as crippling failure. And these two also need to be studied on the aircraft structure. So that's look like, so it's just a pipe and you apply the force, it bow. It's no longer straight. And crippling is a localized failure. So you can pull this, you can push this pipe, you can see it start to wrinkle around the section. So those we call it crippling. Shear is almost similar to the axial force. However, the area is parallel to the force. For axial compression and tension, you pull. So the area that we are concerned is the area 90 degrees to the force. However, for shear, the area is parallel to the force. So apply the force here, both sides, apply here. You are like you make a section, you cut this piece. So that process we call it shear, and you have to shear stress here, whatever to you to get you cut into the material too. Okay, so it's force over area, but area is the cross-sectional area of the pipe. Another one is torsion. Torsion is you twisting. For torsion, when you twist something, you get basically axial stress. Okay, you don't get torsional stress. This is the term we use. However, in reality, we got the shear stress. You twist something, you try to twist, and the failure will be ruptured along the shaft. So it's just ruptured. Just like you pull, you become it's broke into two, but you can also twist the structure. You also have a failure, but normally the failure would be the shear failure. Okay, any question for that? Okay, next is bending. Bending is another unique character. You bend something, what you get, you got stress, is shear stress, either on the top or the bottom, depending on the direction of the bend. If it compress, it's become compressive stress. If it is pull apart, we call it tension stress. So those compression and tension exist for this bending, and we still call this as bending stress. However, it is just like you are study the axial and axial loading, axial stress, which is tension and compression. No different. However, the equation will be the moment where the load apply, time the neutral axis, the distance from the surface to neutral axis. Then you divide by I, which is the moment of inertia. So that is the equation for the bending stress. Okay, any questions so far? So the moment of inertia is calculated by having the formula here. So where we can get, if we're talking about moment of inertia along the x-axis, so B here, the base, time h square, and for the y section is the here, the B time the h. So it depends. For this situation, if we look at B, B is more of the base. Okay, B Remember here, BH cube. I do not want to go into the detail of this, but that's how the bending stress will depending on the moment. The moment become bigger if the distance between the force is bigger, and the distance to the natural axis, and also divide by the moment of inertia. That is how we develop equation for the bending stress. So this is a detailed moment of inertia for the material based on the shape of the cross sections. Okay, questions so far? No. Next, we look at the strain. The strain is a unit, is a ratio. The strain is a ratio of the deformation over the existing length. So, say the length here is 100 cm, and then we pull this part, and then we got like extension of 2 cm. So 2 over 100 cm, 2 cm over 100 cm, whatever the value that you get, those are the strain. So that is how, that is the ratio of the deformations. So what if you got higher strain? Higher strain means the part deform more, and then the L, the total length of the part is maintained. So every time you put a load, the delta, which is the elongation, become more and more. So the strain also increases. So mean easier, if you see the strain number, if the number is big, mean the elongation, the deformation is higher per unit length. So the part, the material is easily deformed. Next is modulus. Modulus is when you test the stress and strain curve. Okay, when you test stress and strain curve. So you got a slope. The linear portion of the graph is a slope. So this slope is stress over strain. Those stress over strain equal to epsilon, which is the stress over strain, which those are the E, which is the modulus of elasticity. Or we can also say the area under curve. So those are modulus of elasticity, or Young modulus, or elastic modulus. You got 3 names to that, so they are the same thing. Why you need the modulus? Because some calculation will be depending on the modulus, the parameter. What modulus means here is the material ability to deform. How fast is deformed with the load. So you can see, if you can see this a bit flat, mean with the smaller force, it deform more. So the material, we can also say, of having that material, we call is more ductile. And material, when you can see lower E, higher E, higher modulus, so mean it is here is slope, so high E, but deform is less. So we can apply strong load, but the deformation is very minimal. So in other words, we can say that material is very strong. This is always the layman term we use when we look at the value of E. So that's why we put in terms of ratio like strain, and here we put into ratio, which is this ratio will give you the strength, indication of the strength of the material. Questions? So let's review again the mechanics of material. We stop at strain, modulus. And for the basic information, why you need to have this strain and modulus, because some of future equation will have this term. By understanding where this term come from, you will be able to understand the equation better. You can use them better. Okay, hold on. Okay, material properties is one of the important thing that you need to understand. Each material will have properties. They call it mechanical properties of material. And then in this example here, we have aluminium and steel. What our interest is, what normally properties give you the density, Young modulus, Poisson ratio, yield stress, ultimate stress, fracture stress, fracture strain, strength coefficient, hardening exponents. So normally what our interest the most is we interested on the Young modulus, Poisson ratio, yield. So this is tensile yield and tensile ultimate. Because this material here, yield and tensile strength here, this is where the material will fail. So this material will fail at 257 megapascal, and for the steel is 364 megapascal. You can see the steel is stronger than the aluminium. So everything that we do, any structure design that we do, we have to calculate the stress. The stress should not be higher than this value here, because this is a failure value. Anything beyond 257 megapascal, the structure will fracture, will be damaged due to the tension load. So there are other value, the shear, the bearing, that one, the detail will go to it when we go to the repair, because those value are given in the structure repair manual. Here, I just try to explain what value, what is mechanical properties of material, what value they captured, and because this is also a part of the renewal for the mechanism, review of mechanism material. So that is something that you just have some brief understanding. We go to the detail when you go to do the repair later. When we will go to the structure repair manual. One of the important thing that also we need to understand is factor of safety. So anything that we do, we have to work on the factor of safety, because factor of safety is a ratio. It will give you straight away how strong is the structure. So what is the ratio? The ratio of the ultimate stress and allowable stress. Ultimate stress is the maximum stress the structure can withstand. Allowable stress is the level that we use the structure to work. Mean that you allow the structure to work to 100 Newton, for example, but you need to design the structure to be able to carry the load for 150 Newton. So 150 Newton over 100 Newton is 1.5. 1.5 is a margin of safety which is required in the design and certification of aircraft structure. It appears in the evidence requirement of the aircraft design, where the factor of safety for the structure should be not lower than 1.5. If it's lower than 1.5, then the structure will not be certified. So in your work later on, when you do the stress analysis, when you do the structure design, and then you do the analysis should show your strength, your design of the repair. The strength is factor safety. The factor safety of the repair is 1.5. If you go lower, you never get the CAM approval for the repair. So again, what is the ratio? Ratio of the design, what the structure need to work on. For example, we have the example of 100 Newton. That's what you design the structure to. But yeah, that's what your structure is supposed to work, supposed to carry 100 Newton, but you design it to 150 Newton, so you will get 1.5 factor of safety. So means that is the meaning of factor of safety. If you see the factor of safety, you can see 1.5, 0.5, 0.5 and 50%. 1.5, sorry, 1.5. 1.5 and 50% mean that the structure that you have designed is 50% higher than the operational load of the structure. So you have to design higher than operational load so that there is a margin. The 50% margin is where you would like to account for the error, account for the environment on the structure can prematurely fail, and also the assumption and design was wrong. So those are 50% available for you to avoid any problem of failure if the structure go beyond what the structure designed for, the structure design capability. Okay, so a lot of people got this wrong. Please understand this well. Again, when you design a structure, you design higher because you don't want it to fail. How much higher is 50%? So how to explain that? You design the structure to work at 100. However, the detailed design, the maximum design load is 150. So it work at 100, but it designs 150. You ratio 150 over 100, you got 1.5. So those are the requirements for the structure. For the design certification of structure, the factor of safety shall be 1.5. Any question, right? And also there's another term, reserve factor, which is allowable load over applied load should be higher than 1. So if we're talking about your structure capable to carry 100, and you design it to 150, so 150 over 100 is 1.5. However, for this reserve factor, we are able to accept higher than 1, that is acceptable, because not all structure to be 1.5, only the major load carrying structure. So any structure like secondary panel, non-structure panel, that those we can allow to be to use reserve factor. Reserve factor should be higher than 1, that is acceptable. Another one is margin of safety, which is the reserve factor minus 1, so it should be more than 0. Anything lower than 0 is not acceptable. Any question on that? Okay, next is the stress concentration. So this one will cover briefly on the mechanics of material. So why we talk about stress concentration? We don't like this stress concentration because stress concentration will give you the premature failure. The aircraft structure part or any structure component under the stress, when you have corners, sharp corners, and small hole, those areas will cause damage because the stresses is higher at the area. So what we can do here, what we need to understand here is the stress maximum. Over the stress, you got a factor of K. K is stress concentration factor. So we look at resolve this K. Sigma max, maximum stress, will be K times sigma, mean that this K is factor. As the K go higher, the sigma max go higher. So we want to lower the K. How to lower the K? So you're not going to have sharp corners, edges, and small hole. So you have to cut everything at a very nice smooth radius for you not to get into the high stress concentration. The highest of the stress, the shorter of the part life. So we don't want to go into that kind of situation. Okay.